Here are some concepts that arise in reliability. The first is reliability versus design complexity. Typically, the more complex the system, the lower the reliability. You have more components that can fail. There are ways to mitigate this problem by placing components, for example, in parallel. But in general, if you take something like a pencil and think about what it is designed to do, and then you maybe take a rocket that SpaceX is blasting off, much more complex system with the rocket and therefore subject to a lower reliability. Second thing is reliable products stand up to stress. Now you can think about this stress in the case of a mechanical item. And off to the right there, you can see there is an axis and there are two normal distributions, bell-shaped distributions. The distribution on the left is the distribution of the stress that we are going to apply to a product, and the distribution to the right is the distribution of the strength. This brings up over-design in the following context. If you have a chair and the load on the chair, let's say, is 400 pounds. So that's what it's rated for. What you can do is you can use over design, and you can design that chair for an 800-pound individual, and therefore you are putting your strength distribution further and further to the right, so the strength and the stress distributions are further apart, and that will increase the reliability. Third bullet here is on consumer perception. Sroli Bratnik had an article titled, "If It's American, It Must Be Bad." Had two identical pieces of RCA electronic equipment, pried the label off of one, replaced it with Sanyo, and it turned out 76% of the respondents said Sanyo was superior with a sample size of 900. So that's the perception. When you go to reality, and this is typical when you look at consumer reports, the most reliable auto manufacturers are Mazda, Honda, Toyota, etc. Very few American-made cars make that top list. The American cars are catching up, but the Japanese got off to a quicker start. These ratings that you see in consumer reports have to be taken with a grain of salt, though, because oftentimes they are only on fit and finish and not as much on how long that particular automobile will last. Another example, room air conditioners. The failure rates from the best to the worst are sometimes 500 to 1,000 times apart. So there's a big difference between low quality and high quality in terms of room air conditioners. Whenever you set up a reliability program, there are always costs, and this goes for quality costs as well as others. The first cost is assessment. You have to go through the extra cost involved with assessing quality or assessing reliability, and that can be quite expensive. Second, if you have a quality control program, oftentimes you need a lot of training to get people to understand quality and reliability, so there's some cost there. The next cost are actions to upgrade the quality, and these are steps that you take, and that might involve this last piece here, which is some scrap and some rework, and items will need to be thrown out or reworked, and there's costs associated there. The advantage to this, though, is you get a reputation for high quality, and that will, in the long term, help you in terms of market share and reputation. The last bullet down at the bottom, reliability can be applied to the service industry. We will talk mainly about manufactured items here, but this is a very, very general notion. If Federal Express says that they will deliver a package by 10:30 the next morning, and it doesn't make it there by 10:30, that would count as a failure. And so you can see that you have a reliability associated with receiving a package by 10:30 from Federal Express. So in the service industry, you also have reliability concerns as well. There are three related disciplines, and these three disciplines share a good bit of the mathematical modeling involved. So the first is reliability engineering, and reliability engineers tend to be interested in the lifetimes of products. Those products could be light bulbs, could be microprocessors, could be airplane wings, could be cranes, could be oil rigs, etc. The second field is actuarial science. Actuaries are interested in the distribution of the lifetime of people on the life insurance side, and they are interested in the lifetimes of structures if you are on the casualty insurance side. Now, in addition to structures, they are interested in vehicles, boats, etc., because those are insured as well on the casualty side. The third group is biostatisticians, and they tend to be interested in the survival times of patients, laboratory rats, etc. The key thing that links these three related disciplines together is you are always interested in a lifetime, and you'll see a little bit later that we will use the random variable capital T to represent that lifetime.